Great. Thank you everyone for making it for today's class. I hope you're gonna pay attention, and as we do always, please try and avoid every distraction that is around you, so that you can really pay attention and follow. So we've been looking at the ideal gas law. We've been looking at gases in general, and we started from the very beginning where we just started talking about properties of gases, the effects of pressure, the temperature, and how it impacts the volume. We started talking about different identities of gases. Then we started developing a theory, or we started going through a theory that was developed that is called the ideal gas law. And that theory suggests that all gases, if we assume all gases to have no volume or no interaction between the molecules, then we can have all gases to be classified as ideal. And that is the ideal gas law. Yeah, and we spoke about if we could classify all gases under ideal gas laws, then we can be able to define the properties of gases under standard temperature or pressure or under certain standard conditions and find the volume of the gas, that is the amount of the gas. We can find the pressure of the gas and can do a lot of fun stuff with that once we can classify them as ideal gases. We went on to now develop the equations of the gases or the ideal gas combined equation. And now we're going to go forward a step further. Last time we used the ideal gas equation to develop the molar mass of a gas and the gas density, right? So I gave you this question from last time to try and solve it on your own. And now we're going to continue right from there. And hopefully you tried this on your own, okay? The whole idea for the ideal gas equation in helping us develop molar mass and gas density is to use the equations that we already know to help us find gas density. Okay, and so this is just a quick review from last time before we move on. And forgive my five. So we started by saying that we already know, and I don't want to solve this for you. I just want to guide you on how you're supposed to solve this. I want you to be the one solving it. So if you didn't do it the other time, please listen carefully. Remember, we said we're looking for. So this question is saying that what is the density of molecular hydrogen? This is very important. We're looking at molecular hydrogen. We said that hydrogen is just the element, but anytime we talk about hydrogen gas, every gas exists, almost every gas exists as a molecule. What that means is that hydrogen, the element hydrogen is just H, right? Now the element hydrogen, which is H, has an atomic number, which is 1. But normally under the element on the periodic table, you're going to see a certain mass that is attributed to the element hydrogen. In the case of hydrogen, the atomic mass of hydrogen is 1.0 something something. Okay, let's check. So remember I told you anytime you are doing chemistry, make sure you have your periodic table close to you because you're going to need it. So let's look at the atomic mass for hydrogen. So what's the atomic mass for hydrogen? I'm expecting that you did this. And so the atomic mass for hydrogen is 1.0078. How do you know this? On your periodic table, you're going to see something like this. And this is the atomic mass, and this is the atomic number. Okay, so this number here is suggesting that the atomic mass for hydrogen is 1.0078. Now, atomic mass is normally represented as the unit for atomic mass is this. Let's look at it carefully. 1.0078 grams per mole. Okay, suggesting that 1 mole of hydrogen is going to have the mass of 1.0078 cancer mole. Keep that here. Keep this here. Very important. So we're saying that what is the density of molecular hydrogen? So coming back to the term molecular hydrogen gas. When hydrogen exists as a gas, it exists as a molecule. A molecule can be formed in so many ways, but most gases exist with a covalent bond. It means one hydrogen is sharing a bond, okay, with another hydrogen. Okay, this is just a simple representation. So we're going to have H2. Okay, the moment we have a molecule H2, then to find the mass of this molecule, we have to go through what we already do. That is a molar mass. Okay, so that is a very important step here. So to find the molar mass of hydrogen, you're going to have this. Okay, and how do we find the molar mass of hydrogen? It's going to be something like this. Because we have two hydrogens, it's the same thing you already know. You take the atomic mass, which is already here, and multiply it by 2. Then that gives you the molar mass of hydrogen gas, or we can call that molecular mass. Anyhow you want to identify that. That's important here. So 1.0078. And let's do this on your calculator. What do you get? I hope you're following me. So let's do it together. And as I said, I'm not going to be doing it for you. I want to guide you, and you are going to do it. So if you didn't do it the other time, this is just a quick review before we start going into what we want to do today. So when you put this in your calculator, what do you get? I'm trying to find my calculator. Yeah, it's here. Good. So if you put this in your calculator, you should get something like surely something that has 2 point something in there. So 2 times 1.0078. Yeah. And I have something like this. If you had something like this, we're on the same page. 2.0156 grams per mole. Okay, at this point, you've done the most difficult part of the whole job, or maybe you're close to getting the answer. That's how I can say. So you just found the molar mass. Okay, this molar mass is supposed to be written like this, but I don't like to write it that way. It's supposed to be written like this so that you can differentiate this molar mass from every other M you know. Okay, and this is H here. So now the next thing is now remember the formula. Remember we used the ideal gas law to derive a formula for gas density. And that formula, if you don't remember the formula, it was D. We had two formulas for gas density. One of them was D equals, who can remember? We had something like this. Your molar mass was here. Okay, let's go back and try and remind ourselves. Oh, no, we're going back. Yeah, this is the formula here. This is one of the formulas for gas density. This was the latter formula we derived. And this was the first formula. They are both the same. Okay, so we have two formulas. Okay, so let's write those two formulas. And that's all you're going to use. Here we have something like this. P up here, then over RT. I hope I'm right. And the second formula, gas density is equal to mass, that is just mass in grams, divided by N here. You still have your P here. And you have your RT. So these are the two formulas here that we use to derive gas density. Okay. So which one do you think we should use here? I'm going to say use this. Why? Because we just found the molar mass, which is here. So you have your molar mass here. What is the pressure? Our pressure is here. But remember, our pressure is in torr. We have our temperature. Our temperature is here. T is here. Your P is here. So we have almost everything we need. What is our gas constant? Remember, I told you there are two values for gas constant. One value is 8.314, but that value is in kilopascal. Kilopascal is in kilopascal liters per mole per Kelvin. If you use that, it means your pressure should be in kilopascal. If you don't want to use that, you have to use the other one, which is 0.08206. Yeah, you have to use this one. This one uses ATM liters per mole per Kelvin. So you choose the one that links itself best to the unit you have. 0.08206. So one of these values you're going to use for your R. I'll suggest you use this because this one is in ATM, because then you can change your pressure into ATM. Okay. So whichever R unit you have, just pick, and now you just substitute them into the formula. Okay. Remember, you're going to have to change your temperature to Kelvin, as we do always change temperature into Kelvin. You change your TOR into ATM. Then you can solve this. Okay, so this is what I'm expecting you to do. As I told you, I won't solve for you. I was just trying to guide you to understand what we're doing. And so if you did all of this, then you're on the right track and your answer should be correct. Okay. If you did something different, you should be able to defend what you did. I'm not going to say you're wrong. You just have to defend what you were doing. So what were you doing? What was the answer you arrived at? You're supposed to get something like 0.0847 grams per liters. That's what you're supposed to get. Your answer is supposed to be that. And I want to see how you went about it. You see, I just explained to you what you're supposed to do. I don't want to do it for you. You should go try it. And your answer should be something like this: 0.0847 grams per liter, where G is standing for the mass, L is standing for the volume. Remember, density is just equal to the mass over the volume. Great. So hopefully we all did something like this, and hopefully we all on the right path to getting the answer. Great, great, great. So this is just a quick review. I wanted us to go over what we've been doing. Okay. And remember the main formulas the main formulas we arrived at, keep that in mind. Okay. The main formulas we arrived at was what? We derived the density formula from the ideal gas equation, which we said is what? Molar mass pressure divided by what? Gas constant temperature. That's formula 1 for gas density. Or formula 2, which is equal to what? We have the mass of the gas multiplied by the pressure of the gas divided by the mole of the gas multiplied by the gas constant multiplied by the temperature. These are the two formulas we derived from last time, and we applied those two formulas. So we want to take this one step further. Sorry. I want to take this one step further. Okay, so are you ready? I hope you're ready. Make sure you have your I nearly said make sure you have your Bibles with you. Sorry. I have my Bible with me, that's why I said that. But make sure you have your calculator, make sure you have your periodic table, and make sure you have your chemistry thinking hat on. I need you to be able to engage the material you're doing. I want you to think about the things I say, ask yourself questions, and ask me questions too. Maybe you don't understand what I'm saying, just ask me questions. You can send me a question through email or whatever you want to do. Great. So we're going to take this a step further. We want to be able to identify why are we doing all of this. All the reason why we're doing it help us to identify an unknown gas. Okay, so let's see. There's a gas present. Okay, If we can know, if we can know the mass of the gas or the pressure that the gas is exerting or the volume of the gas or even the temperature at which that gas is being exerted, we can be able to find the molar mass. And every gas, based on the what we learned about the periodic table, every gas is unique. You see, on the periodic table, we have so many different gases. They are unique because of their elements that constitute the gas. So if we can find the molar mass, we can be able to predict which gas is present, even if we don't know, because we can find the molar mass. And when we find the molar mass, we can compare the molar mass to whatever mass is on the periodic table, and that helps us to know the identity of the gas. Does that make sense? So one of the reasons why this is important is we can identify unknown gases, and that is great. That is so great. So let's dive into this. Let's see how can we identify the gases. If you've been following, you already know where I'm going with this. We already derived a formula from this that helped us to involve molar mass. But this time we want to make molar mass the subject. Okay, so let's go again. Remember we said that the molar mass just compares the mass of the gas per mole, right? Now anytime you see mole here and we have a mole here, it means that we can change our ideal gas to make it to get a smaller mass. Now this M is supposed to be like this. Once again, I'm just reminding you. We write it this way so that it can differentiate. It's the same. This is molar mass. So you know what? Let me just write it well. I don't want you to be confused. And all this while I've been using big M because I didn't want to draw that. Oh, what did I just do? No, no, not highlighter. Oh no, Gideon, what are you doing? Yeah, just highlight, not highlighter. So this is the M we're supposed to be using for molar mass. Yeah. So we have N here. That's standing for the mole. So let's first thing we want to do, let's convert this formula into moles. Then we can put that formula into this. So PV equals nRT. If I wanted the N to stand alone, I'm going to take PV equals nRT here, right? And I'm going to divide this by RT and divide this by RT. And I'm going to cancel out. Then now I have only N standing alone, and N is equal to what? PV over RT, right? Great. Now that I have N to be standing alone, then now I'm going to try and put N into this formula, okay? How do I put N into this formula? Let's see how that goes. So we had this, and we have step 2 here. Let's go to step 3 here. In step 3, I'm just going to substitute N in that formula. So we're going to have something like this. We're going to have molar mass to be equal to, I have mass, right? I have mass. You can write that as mass multiplied by 1 or, oh, sorry, no, 1 mass multiplied by N, okay? Now instead of N, I'm going to put this here. So we can have molar mass. Really struggling with this molar mass. Nope, multiplied by, now, this is 1 over N, okay? 1 over N is the same as the inverse of your N. Now our N is PV over RT. So 1 over N means that's just the inverse of this. So what would the inverse of the N? Because we're saying N is equal to PV over RT. And we want the inverse of N. The inverse of N straight away is going to be what? RT rather on the top here divided by what? PV. Great. Right? So now we can write our molar mass to be equal to what? M R. Oh, no kidding. What are you doing? MRT divided by PV, and that's our final answer here. So molar mass is equal to the M mass multiplied by the gas constant multiplied by the temperature divided by what? The pressure multiplied by the volume. And just like that, we will have been able to derive another formula that helps us one step further. And this formula is going to help us to be able to identify unknown gases. That's the whole goal. Because if we can know the pressure of the gas, if we can know the rate of the gas, and we already know the gas constant is a constant. If we can know the temperature at which that gas is exerting that pressure and the volume of the gas, we can find the molar mass. And when we find the molar mass, we will have an idea of which gas we're dealing with, or we can identify an unknown gas. Okay, so this is a formula we're deriving for molar mass. Now you want to keep that formula close to you because, as we said, this can guide us in identifying unknown gases. So if we have a situation of a gas which is unknown, through this formula we can be able to identify that unknown gas. Okay, great, 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 great. So we want to move on. Let's see what we can do with this. Great. So from the formula we just derived, then we can now go a step further to talk about something called determining the molecular formula of a gas from its molar mass and empirical formula. Now this is important here. Empirical formula, molecular formula, it takes us back to takes us way back to stoichiometry. Now, if you remember, we started talking about stoichiometry, and when we were talking about stoichiometry, we said something very important. Okay, molecular formula here is just it's a way of describing a compound, right? So let's say I have a compound. I can describe the compound with only the symbols of the elements and numbers that suggest the ratio with which the different constituting elements are reacting. Okay, so for example, if I have something like C2H4, okay, C2H4 is just elements, it's just two letters and two numbers. But behind these two letters and two numbers, it is telling me so much. It's telling me so much about a particular compound here. It's telling me that this compound has two carbons and this compound has four hydrogens. And this is what we call a molecular formula. Okay. Now, molecular formula is the big picture. Now, the subset of molecular formula is something we call empirical formula. An empirical formula is just like the molecular formula, but your empirical formula gives you the simplest whole number ratio. Okay, so if I wanted the empirical formula of this molecular formula, what do you think it's going to be? Remember, I said it's the simplest whole number ratio. So we're going to have the simplest whole number ratio is just going to be CH. This is just an example I'm suggesting, CH2. How do I know that? Simplest whole number ratio means that we can reduce this down. 2 can go into itself 1 and 2 going to 4 2 times. We're just reducing this to the simplest whole number ratio. And once you reduce to the whole simplest whole number ratio, you get something called empirical formula. That didn't go well. I'm going to clean this. So this is just explain to you the difference between molecular formula and empirical formula. I hope that makes sense. So your molecular formula is the big picture describing the different constituent elements and amounts of those constituent elements in the reaction to form that molecule. Now your empirical formula is just the simplest whole number ratio of your molecular formula. So when you simplify your molecular formula, you get the empirical formula, suggesting to you the simplest whole number ratio of the elements that are combining in that molecule. Okay, great. I hope that makes sense. So we're saying that we want to be able to determine these two things, the empirical formula and the molecular formula, using the knowledge we just derived. We were just able to use the ideal gas equation to derive the molar mass. And now we want to use that knowledge to help us determine the molecular formula of a gas. So I have a gas, I can find the molecular formula and even the empirical formula. So let's see how this works. And remember, this should remind you of stoichiometry. By now, you've realized that everything we learn in chemistry, we don't throw it away. That is why I need you to understand what you're doing. If you didn't understand what you were doing previously, you're going to struggle to understand what you're doing going forward. So I'm really hoping you didn't just forget about everything we started learning, because we started learning stoichiometry many weeks ago. All those things are important as we go forward. As we go forward and learn about acid bases and reactions of acid and bases and all of that, you're going to realize that, oh, okay, everything I learned is important and I need to use it. So I hope you don't forget all the things you've been learning. It's important. Okay, so let's go into this. So we're saying that cyclopropane, a gas, once used with oxygen as a general anesthetic. Now I'm going to leave you to figure out what is an anesthetic. Go and read what is an anesthetic. Okay. Now we're saying that this anesthetic, you know what, let me help everybody. What is anesthetic? Who can help us? Who knows what an anesthetic is? I'm going to ask you to find what an anesthetic is in the video, so get ready. What is anesthetic? Now, if you don't know anesthetic, it's where we get the anesthesia. And now by now, if you know anesthesia, if you've ever gone to the doctor's office, oh no, when you're doing when you go to the doctor's office, do they give you anesthesia? Well, if you're going to do a very operation that is very harsh, or it's going to bring about a lot of pain, scientists have been able to develop something called anesthesia that is going to make your muscles and your nerves not sensitive to the pain. So they're going to induce you with a certain chemical that is going to make you insensitive to pain, so that you're going to see them cut you open and slice you up and do all the things they need to do, but you can't feel the pain until you're done. I don't know if that's a good thing or not. I'll leave that to you. If you have any stories of anesthesia, I'm going to ask you in the next class. Next week, I'm going to be able to teach live, and I want to hear some of your stories. But I have not been an anesthesia, so I don't know what it is. But I remember my mom said she gave birth to, I have two other siblings, and she gave birth to all of us during a cesarean session. So it means they cut her open 3 times to bring all the three of us out. I am thinking they use anesthesia. I don't know. I don't know how that works. So please, all those who have the information, be ready to share with us in the next class. But basically, we're saying that this anesthesia, when you're using this anesthesia some time ago, it was composed of cyclopropane used together with oxygen. So it means all your learning is not abstract. Okay, great. So this anesthesia is composed of 85%, 85.7% carbon. This number is important. Keep that in your mind. And 14.3% hydrogen by mass. And this is very key. It's telling us by mass. We're going to use all the information we're reading. Find the empirical formula. So they want us to find the empirical formula. Find the empirical formula. After you find the empirical formula, now they're telling you if you have 1.56 grams of this anesthesia and it occupies a volume of 1 liter at a temperature of 0.984 atmosphere, sorry, at a pressure of 0.984 atmosphere and at a temperature of 50 degrees Celsius, what will be the molecular formula of this anesthesia, which is called cyclopropane? Interesting. So let's say I don't know what cyclopropane is. I'm going to find the molecular formula and empirical formula of cyclopropane, and that's exciting. So let's get into this. We want to find the empirical formula. That's the first thing we want to do because that's the first thing they're asking us to do. To be able to do that, we want to pay attention to the information they give us. They're telling us that, remember, I told you the empirical formula just gives you the simplest whole number ratio. So keep that in mind. Simplest whole number ratio of the constituent element involved in the reaction or in the reaction to give you that compound. So we already know that our compound, which is cyclopropane, it is made of two things, carbon and hydrogen. So we are one step closer to finding the empirical formula. We already know that it's carbon and hydrogen, right? We already know it's carbon and hydrogen, but now we want to find out what is the ratios, the simplest whole number ratio. So let's start. We want to start with carbon, okay? We were told that the percentage by mass means that if the total compound was 100 grams, let's say, because it says percentage by mass, if the total compound was 100 grams, 85.7 grams of that compound will only be carbon, and 14.3 grams of that compound will be hydrogen. So let's start with C for hydrogen. So I have 85.7 grams to be hydrogen. I want to find the ratio. To be able to find the ratio, we need to know the moles of carbon that would have been in this. And to help us do that, remember, remember the formula we've been using always. We said molar mass. Remember the base formula for molar mass is what? It's mass over mole. And from this, we can find mole to be equal to, just substitute this, and you're going to have mass over molar mass. Great. And that should give us mole. Okay, so let's do this together. What is the mass we have here? The mass is 85.7 grams. Oh no, 85.7. Gideon, what are you doing? 85.7. Good. 85.7. Great. 85.7. 85.7. Good. Now, what is the molar mass? Everybody take your periodic table. You're looking at carbon. We're talking about carbon. So look at carbon. What is the atomic mass for carbon? It's going to be that mass that is sitting at the bottom of carbon on your periodic table. And you should have something like 12 point something. 12.001. So I have 12.00. Oh no, 12.01, not 00. So if you're having this, you're doing it with me. Let's go through it. 12.0 one, one, something like that. Now put this in your calculator. What do you get? 8.57 divided by 12.011. Let's do this together. So I have 85.7 divided by 12.011. If you're with me, you're supposed to be having an answer like 7.135, something like that. So that's what I had. I had 7.13, oops, 5. In three decimal places. That's what we're doing now. For the mole. Okay, so remember we said that so this is the mole representation for the mass percentage of carbon. Now we're saying that empirical formula is the simplest whole number ratio. So we're going to go a step further. We're going to divide. We're going to divide. So we're going to hold on to this. Hold on to this. Hold on to this mole. We're going to use it very soon, but hold on to it. Okay. Now let's do the same thing for hydrogen and see what we have. Okay. Okay. For hydrogen, I'm going to write hydrogen H. Okay, and they're telling us that by mass, we're going to have for this cyclopropane, we're going to have 14.3 grams to be hydrogen. Okay. Okay. Now we already know the same. We're doing the same thing here. We said molar mass is equal to mass over mole, or you can go straight away and make mole the subject because we're finding the mole, and we're going to have mass over molar mass. Wow. Okay. And now let's do this. Take your periodic table. Oh, we're gonna have, what is the mass? We said it's 14.3 grams divided by the molar mass. And that should give us the mole. What's the molar mass for hydrogen? We did it the other time. It's supposed to be what? 1.008, something like that. If you don't remember, look on your periodic table. It's 1.007. 1.0078, something like that. Okay. I put this together, and what do I have? So let's put this. Take your calculator and let's do this together. I have 14.3 divided by 1.0078. Great. And I have something like this. I have 14.189, something like that. 189. For the mole, of hydrogen. Now, because we are looking for the empirical formula, we're going to take, we're going to divide by this. We're going to divide each of them by the smallest number. Okay. So for carbon, we're going to divide. For carbon, we're going to divide 7.135 by the smallest number. What is the smallest number between the two of them? It's still 7.135. Okay. And this will cancel itself by 1 because any number divided by itself is 1, right? So we're going to have 1, and that is for the ratio in respect to carbon. Now let's do the same thing for hydrogen. Now, because hydrogen is the bigger number, we're going to divide the bigger number by the smaller number. For hydrogen, we're trying to find the ratio, and you're going to have this to be equal to what? You're going to have this to be equal to 14.1, oops, 189 divided by what? The smallest number. What's the smallest number? 7.135. And what do you get from that? Your calculator. 14.189. And I'm encouraging you to be doing this with me. If you just sit down and watch me enjoy this alone, you might finish and still not understand what is going on here. And if you did this, you're going to get 1 point something, 1.9, in fact, 1.99, two decimal places. Now, we round this up and we're going to get 2. So the ratio for carbon to hydrogen is 1:2. So then our empirical formula is going to be, I don't have space, so let me go to the next one. Our empirical formula is going to be what? C1H2. And that is the empirical formula. Okay, great. So that's just the first step, if you remember. Yeah, this is just the first step. So now that we're going through the first step, that's great. We've been able to solve the empirical formula, the first step. Now let's go to the next step. The next step is that, okay, you found the empirical formula, great. You're saying that now if you have this mass, you have this mass, you have this volume, you have this pressure, and you have this temperature. What is the molecular formula? Okay, remember we found to be able to find the molecular formula, we have a formula that helps us to find the molar mass. Why do we need to find the molar mass? Because the molar mass, in this term, we're dealing with a molecule. So the molar mass is going to be the same as the molecular mass. And once we can find the molecular mass, we are a step closer to finding the molecular formula. So let's try and find the molar mass for this. If you don't remember the formula, it's the one we derived from the ideal gas equation. Molar mass, in this case, is the same as molecular mass. It's going to be equal to the mass multiplied by the pressure. If you don't know what I'm talking about, let's go back. This formula is what I'm talking about. Great. So multiply by the rate constant, sorry, gas constant, not the rate, gas constant, divided by the pressure and the volume. And before you move on straight away, know that we need to change our temperature to Kelvin. Keep that in mind. So we're going to change this Celsius to Kelvin. How do we do that? Anybody can remember that? You'd go ahead and add plus 273. Great. So just add plus 273 to your Celsius, plus 273. You add plus 273.15, something like that. And that should give you Kelvin, okay? So hopefully someone can do that for us real quick. Great, thank you. So if you add 273.15 to 50 degrees Celsius, what do you get? Anybody? You're gonna get something like 323.15 Kelvin. 3 oops, sorry. 323.15 Kelvin. Great. Now we can go ahead and substitute. Now all you have to do is just what? Substitute. Take your equation and just substitute. So let's do this. Molar mass or molecular formula is going to be equal to, what's our mass? Our mass has already been given in grams. It's 1.56 multiplied by, what's our gas constant? Remember, you have to choose between the gas constants you want to use. I am going to go with the gas constant that has ATM, because my pressure is in ATM. So I don't have to do any conversions. So that gas constant that has ATM, it's the one that has 0.082. I wonder why I'm writing so big. 821, 0.821 liters. The units are a lot, so let's deal with this. ATM per Kelvin. You don't have to write all of these units, but I'm writing them because we're going to divide them by each other. Per mole. I'll multiply this by your temperature. What was our temperature? 323.15. I don't have space. I'm just going to write 323 here. But it's 0.15 Kelvin. Now the first thing that's going to happen is that the Kelvin that is here. Oops. Oh no, I don't have space. Good. This Kelvin is going to cancel out this per Kelvin. So this per Kelvin is going to be cancelled out by a Kelvin. Because per Kelvin simply means 1 over Kelvin. And this is just Kelvin. So 1 over Kelvin multiplied by Kelvin is going to cancel out. That's the first thing here. Now divided by what's our pressure? What's our pressure? Our pressure is 0.984 ATM multiplied by our volume. What's your volume? 1 liter. Straight away, this liter here is going to cancel this liter. This ATM is going to cancel this, and this is why I read the formula, so that you know that it cancels out every day. Once your units match, it means you're doing the right thing. So look at the units we're left with. We're left with grams here, and we're left with per mole. Per mole is the same as 1 over mole. And that is right. We're solving for molecular mass. We're supposed to have grams per mole as our answer. Now let's put everything in the calculator, and you should have your answer for this. And we are one step closer to finding the molecular formula. Now the molecular formula helps us to identify the gas we're dealing with, and that's the whole point of what we're doing. Okay. Okay, so let's go. So I have 1.5, 1.56, 1.56 multiplied by 0.00821 multiplied by 323.15 divided by 0.984 multiplied by 1. And what do we have here? Good. Great. And we should have our answer here. So let's see here. I think that I'm missing something here. I think I'm missing something here. Wait, let's look at the value for the gas constant. Is 0 point, let me see. Let's look at the formula for the gas. Let me look at the gas. I want to make sure everything we did is right. Uh, the value for R, yeah, is 0.82. Yeah, 0.0821. So we're right. We're on the right track. And what answer did you get? My calculator is giving me an answer that I don't trust. Okay, so let's go over this again real quick. Let me go over this real quick together again. So calculator, let's do this one more time. So my mass is 1.56 multiplied by my gas constant, which is 0.0821 multiplied by my Kelvin, which is 323.15 divided by what is my pressure? My pressure, which is supposed to be in ATM. Pressure ATM is supposed to be 0.984 multiplied by what's my volume? My volume is 1 liter. Yeah, good. Now I'm getting the right answer. Yeah, I was very confused. Yeah, I'm supposed to get 42. If you had 42, you're right. My calculator was giving me an answer that I was not expecting. Good. So we're supposed to get 42.06, something like this. Grams. Remember, our unit left is what? Grams. There's grams here and there's per mole. Per mole means divided by mole. That's the meaning of per mole. Okay, good. So this is going to be our molecular mass or molar mass, however you want to call it. Because this is a molecule, you can call it molecular mass. We are one step closer to finding our molecular formula. Okay, so we just found our molecular mass, which will help us find molecular formula. So this is the final stage. And the final stage here is to know this. Okay, so this is what you should know. Remember, we said that the empirical formula, which is EF, is just the simplest whole number ratio. The molecular formula is the big or the bulk representation or the actual representation of the ratios of the compounds that are involved, ratios of the elements involved in the compound. Okay, so the big thing that relates your molecular formula to the empirical formula is the molar mass. The mass gives you the actual values. Your empirical formula gives you the simplest whole number ratio. Okay, so we can write this. Okay, that the empirical formula, if you have the molecular formula, or sorry, the molecular mass, if you divide the molecular mass by the empirical formula, the mass of the empirical formula. So let me write this as the mass of the empirical formula. That gives you the multiplier. It's going to give you a certain number. Okay, this number is a multiplier that can result in your molecular formula. Let me call that multiplier. What I mean by multiplier is, remember we said that this is the simplified form and this is the bulk form. So if I want to get the bulk form and I know the simplified form, I need a multiplier. Just when you have the multiplier, that multiplier is going to get you to the molecular formula. So we want to find the multiplier. What is the mass of the empirical formula? Some people, you can call that empirical mass. Remember we said that the empirical formula we had was CH2. The mass of this, so we're looking for the mass of the CH2. Look on your periodic table. Let's do that real quick. It's going to be something like this. C is what? 12. 12 points. Look on your periodic table. What's the mass of C? What's the mass of steam? What did you get for the mass of steam? It's 12 point something. Let's go periodic table. What's atomic mass for carbon? Anybody wants to help us? It's 12.01. Let's say, okay. So carbon plus, we have 2 of hydrogen. So let's say 2 times, who remembers the atomic mass for hydrogen? It's 1.0078. So let's say 1.08. 1.0008. Good. Chemistry has a lot of decimals, and you have to be happy about that. So we're trying to find that mass of the empirical formula. So we're going to have so we're going to have 12.01 plus 2 times 1.008. Good. And we should have like this, something like this, 14.026, something like this. Okay, great, great, great. So we are almost there. So now we can find our multiplier. Our multiplier is going to be our molecular mass, which we just found. What was our molecular mass? 14.076. So we're going to have our multiplier to be 14.06 divided by, sorry, it was not 42.06. Sorry, I nearly made a mistake here. Our molecular mass we just found was 42.06. So let's write that down. 42.06 divided by, what was the mass of our empirical formula? The mass of our empirical formula was 14.026. And that should give us a multiplier that can help us find our molecular formula. What is that multiplier? Let's do this together. We have 42.06 divided by 14.026. Good. We have 2.99, which can be approximated. That sign means approximated to what? 3. So our multiplier is 3. Okay, so now we are almost close to the empirical formula. We said that, sorry, almost close to our molecular formula. We said that to get the empirical formula, so to get a molecular formula, when you have, it's just multiply it by what? The multiplier. I'm just using m, this small m, to stand for the multiplier, and that should give us the molecular formula. Okay, great. So let's do the same thing we just wrote here. So this will now be equal to what? What was our empirical formula? Our empirical formula we just solved earlier was CH2. Our multiplier is what? It's 3. And that should give us our molecular formula. So 3 multiplied by the C, which is only 1. C has just 1 here. So 3 times 1 is 3. So C3. Now 3 times 2 is what? 6. H6. And that is the molecular formula, which is the bulk representation of the ratio. So we just solved for this. If you want to, I wish I had more space. No, if I had more space, I was going to show you something. So what this means is that we have 3 carbons, okay, and they are in a chain. We call that a cyclic chain. We're going to do more of that when we talk about structures of molecules and bonding. We're going to see something called cyclic. So that's why the name cyclo means that it forms a cyclic chain. And we're going to do more of that. But we just used our understanding of the molar mass from the ideal gas equation to be able to identify the molecule. So we didn't know the molecular structure of the molecule, but we just found the molecular structure. How? Because we just found the molecular formula. With this molecular formula, we can draw the structure of this particular anesthesia or gas called cyclopropane. Great, great, great. So if you're following me through, we just found the identity of this gas. Its empirical formula was CH2. Its molecular formula is C3H6, which is called cyclopropane. Great. So because of time, I'm going to ask you to try this on your own. This is we do. And I want you to take your time. You can pause this video, go backwards, rewatch it, follow the steps, apply the same steps, and you should have an answer. Okay? Great. So this is going to be for you as your exit ticket. I don't want to throw more information on you. I want to see you try this in your notebook. Okay? Follow all we did and you should arrive at a very good answer. I hope you're able to get through this, and I hope you have a great rest of your week. I want to just quickly touch on this. This is important for me. If you're having issues, if you're having issues, remember every Tuesday, every Tuesday, once again, every Tuesday and Thursday from 3 p.m. to 3:30, I'm available. I've been sitting there waiting for someone to show up. Nobody shows up. You have issues with your Canvas, you have issues with your Beyond Labs, you don't understand something in class. This is the time to see me, okay? So hopefully somebody shows up. I hope you have a great rest of your week.